afternoon, all of you. Today in this class, we are going to discuss about the next concept, that is nurse depression. Nurse depression. Before going to discuss this one nurse depression, first we will see what we have discussed in the standard hydrogen electrode. Standard hydrogen electrode. What we have discussed in the standard hydrogen electrode? Standard hydrogen electrode can act as both anode as well as cathode, whereas it may act as cathode or anode. In cathode as well as anode, anode of cell value is assumed to be 0 for the standard hydrogen electrode. Standard hydrogen electrode can act as cathode as well as anode, whatever may be cathode or anode, when anode of cell is assumed to be 0 for the standard hydrogen electrode. Standard hydrogen electrode, we have seen some conditions. What should be the concentration of the HCl? 1 m. Then only it will become the standard 1 m. Correct? All the ions concentration should be 1 m. Then only it will become the standard one. Now, here in standard hydrogen electrode, we seen the few applications also. It is used to determine the reduction potential of half cells. Reduction potential of what? Half cells. For example, if you want to determine the reduction potential of the copper half cell, that copper half cell is connected with the standard hydrogen electrode. This copper half cell is connected with the standard hydrogen electrode. Then you can easily calculate the standard reduction potential for the half cell. Here I am taking copper half cell. When this copper half cell is connected with the standard hydrogen electrode, we will get the standard reduction potential for the copper. Right? Means here I am telling that standard. What is the condition? Now, here we are using which solution? Copper sulfate solution that we have discussed in the applications of the standard hydrogen electrode. Correct? Now, I am taking which solution? Copper sulfate solution. What should be the concentration of this copper sulfate solution? 1 m. When you are connecting the half cell with the standard hydrogen electrode, the concentration of the other solution should be 1. Then only we can calculate the standard electrode potential. If you want to determine the reduction potential of the another half cell, for example, zinc half cell. Zinc. Reduction potential. Just think. Zn plus 2 to Zn, that is reduction. E means potential, not means standard. Standard reduction potential for the zinc half cell. When this zinc half cell is connected to the standard hydrogen electrode, this one is half cell, standard hydrogen electrode is another half cell. Right? Now, where we took which solution? Zinc sulfate solution. Zinc rod is dipped in zinc sulfate solution, that will become the zinc electrode or zinc half cell. Like a zinc sulfate solution. What should be the concentration? 1 m. Means what is the condition for the standard hydrogen electrode for determining the electrode potential of the half cells? The condition should be concentration of all the ions should be 1. Concentration of all the ions which are present in the solution should be 1. Then only we can determine the electrode potential, standard electrode potential. Now my doubt is, what is doubt is, if this concentration is not equal to 1, what happens? If the concentration of CuSO4, right, that we have taken in the solution in the beaker is not equal to 1 m, what happens? How to calculate the electrode potential? If the concentration of this zinc sulfate is not equal to 1 m, which is not equal to 1 m, any other concentration, then how to calculate the electrode potential? Now it is not standard. Now it will be only electrode potential. Electrode potential for the copper half cell, electrode potential for the zinc half cell. Right? It should not be connected with the SHE because here we are taking standard, whereas here there is no standard because the concentration is changing from 1 m to any other concentration. Here also same, the concentration is changing from 1 m to any other concentration. Means when the concentration is 1 unit concentration of all the ions which are present in the solution, then only we can use the standard hydrogen electrode for determining the electrode potentials. If the concentration is not equal to 1 m, we cannot use the standard hydrogen electrode for calculating the electrode potential. Means what I am telling is, by using standard hydrogen electrode, we can calculate the electrode potential of the only solutions whose concentration is 1. Whose concentration is 1 m. If the concentration is not equal to 1 m, then we cannot calculate the standard electrode potential or reduction potential by using the standard hydrogen electrode. In such cases, how to calculate the electrode potential when the concentration of the solution is not equal to 1? Not equal to 1. We have to use the one equation. That equation is called as what? Nernst equation. Means if the concentration of the solution is not equal to 1, then use Nernst equation. If it is exactly equal to 1, then we can use standard hydrogen. Clear? Now we will see the Nernst equation. What is meant by Nernst equation? It is the one of the equation. It is the equation. We will see equation later on. It is the equation which is used to determine the reduction potential. Reduction potential, or it is also called as electrode potential of cells. Half cells. Half cells means in electrochemical cell we are using two cells. This one is one half cell. This one is another half cell. If we connect to both, what happens? It will become the complete cell. Complete cell means we can determine the electrode potential of the only half cells by using the Nernst equation, as well as and total voltage. Total voltage, that is E cell also, complete cell also, E cell, electrode potential of the complete cell by using the Nernst equation. By using the Nernst equation means by using the Nernst equation you can calculate the reduction potential or electrode potential of the half cell, as well as the cell potential, total complete cell voltage, that is called total voltage or EMF, by using which equation? Nernst equation. For which cells? Electrochemical cells. Electrochemical cells at equilibrium. That is the condition at equilibrium. Now here, no need to be the concentration of the solution equal to 1. Whatever may be the concentration of the solution, by using Nernst equation easily you can calculate the reduction potential for the half cell as well as the reduction potential of the complete cell by using the Nernst equation. Now we will see the Nernst equation. Now I want to derive the equation, that is Nernst equation. It is not important for the exam. Derivation is not important for the exam. Then also just we will see how it is derived. Derivation of Nernst equation. Derivation. In the first year, we have studied equilibrium chapter and thermodynamics. In that, we have studied that delta G is equal to minus MF E cell. And calling this one as equation 1. In the last year, that is for PUC, we have studied delta G, equilibrium and thermodynamics chapter. In that chapter, we have studied that delta G, change in Gibbs energy, equal to minus NF E cell, equation 1. If the concentration of this cell is exactly 1, of the solution is exactly 1, then it will become standard. That is delta G naught is equal to minus NF E naught of cell. E naught of cell, E cell. What is the difference? Here concentration of the solution, what we are taking, that is not equal to 1. Therefore, I am taking E cell. Right? E naught cell means what? Here the concentration of all the average approaches in the solution, which are present in the solution, equal to 1. That is standard 1. Equation 2. This one is equation 1. Equation 2. From thermodynamics, we have studied one important equation. What is that equation? Is delta G is equal to delta G naught plus RTNF. RT log Kc. Sorry, log Kc. This one we have studied in thermodynamics. Delta G is equal to delta G naught plus RT log Kc. Kc means equilibrium constant. Just think here, natural log is there. Log base E is there. Or I can write ln Kc. Ln Kc, natural logarithm, that is base E is there. Right? Delta G is equal to delta G naught plus RT ln Kc. Here base E is there. Right? Now, since we know that delta G is equal to this much of value is there, delta G naught is equal to this much of value is there, just substitute equation 1 and 2 in equation 3. Equation 3, I am calling this one as equation 3. Put equation 1 and 2 in equation 3. Put equation 1 and 2 in equation 3. What happens? In place of delta G, we can write minus NF E cell. Minus NF E cell is equal to, in place of this delta G naught, I can write minus NF E naught of cell. Minus NF E naught of cell. Plus as it is, the value also as it is same. T ln Kc same. Just what I have did is, in place of delta G, I am writing minus NF E cell here. In place of this delta G naught, I am writing minus NF E naught of cell. That is the thing. Now we will see what is the equation here. Minus NF E cell is equal to minus NF E naught cell plus RT ln Kc. Now here, just multiply with the minus to the equation, both left side as well as right side. What happens? It will be minus into minus plus NF E cell. I am multiplying with the negative sign. Now is equal to minus into minus plus NF E naught of cell plus into minus RT ln Kc. Now divide the equation. Divide equation by NF. Divide this above equation by the NF. What happens? NF get cancelled. It will be E cell is equal to, here also NF is there. We are dividing with NF divided by NF divided by NF divided by NF. Whole equation is divided by NF. And here NF get cancelled. What is the here? E naught of cell. Now minus RT by NF. Here there is no NF. Therefore we are dividing with the NF. It will become RT by NF ln Kc. Kc is what? Equilibrium constant. Equilibrium constant. Now I want to convert this natural log into the log based term. Correct? Here I want to convert this ln E to the log 10. Log 10. Right? What should I have to multiply is 2.30. Means ln E. The base E is converted to base term by multiplying with the 2.303. Right? That is ln E is equal to 2.303 into log 10. What happens now? Here it will be E cell is equal to E naught of cell minus, I am writing 2.303 into RT by NF. Now it will become log 10. Then E base E is converted into base 10 by multiplying 2.303 into Kc. This is called Nernst equation. This equation is called what? Nernst equation. This is the Nernst equation. Now, here E cell is equal to E naught cell minus 2.303 RT by NF log Kc by 10. Now, we know that the value of R is, R means what? Universal gas constant. It has fixed value. How much it is? 8.314 joule per mole per Kelvin. Right? Now, I am getting divided by per mole per Kelvin. 8.314 joule per mole per Kelvin. Now, this is the value of universal gas constant, that is R. Now, temperature I am taking in terms of Kelvin. Here I am taking standard one, that is 298 Kelvin. Room temperature I am taking as 298 Kelvin temperature. Now, F means Faraday's constant. What is the value of Faraday's constant? It is 96,500 coulomb of charge. Coulomb of charge. If you substitute these values in the equation here, in place of R, you are writing 8.314. In place of temperature, you are writing 298 Kelvin. In place of F, that is Faraday's constant, if you are writing 96,500 coulomb. After simplifying all these things, you will get the one value. That is, I am writing directly here. Now the equation will become E cell is equal to E naught of cell minus, when you multiply 2.303 with 8.314 into 298 Kelvin divided by F means how much? 96,500. You will get value, that is 0.05291. N means number of electrons involved in the reaction, and that is N only. N into log Kc. This one is also known as Nernst equation. Here constant I have not substituted. Right? Here I put those constant values and simplified. Here the value is 0.0591. Right? Now here I am writing directly constants R, E, etc. Here I have simplified that one, that is 0.0591 by EM. Now we will see E cell means cell potential. E naught of cell means standard cell potential. Now here N means number of electrons involved in the reaction. For 10 cell, 2 electrons are involved. We will see later on. Kc means equilibrium constant. Now once again I will explain this one. Now just say Nernst equation. When we have to use the standard hydrogen that cells SHG, standard hydrogen electrode, when the concentration of the given half cell is exactly 1, then only we can use the standard hydrogen electrode for determining the electrode potential of the half cell. If the concentration of the given solution is not equal to 1, then go for the Nernst equation. Then you can calculate the electrode potential of the half cell or complete cell by using which equation? Nernst equation. Means Nernst equation is used to calculate the electrode potential or reduction potential of the half cell or complete cell in the electrochemical cells at equilibrium. Right? Now we will see the equation. How to derive this one. In the first year, we have studied equilibrium factor as well as thermodynamics. In that, I am taking few data. Here we know that delta G is equal to minus NF E cell and delta G naught is equal to minus NF E naught of cell. I am calling this one as equation 1. I am calling this one as equation 2. As well as from thermodynamics, we know that delta G is equal to delta G naught plus RT lambda Kc. R and T are constant, universal gas constant. This one is temperature, that is also constant. Kc means equilibrium constant. Now just think, I am putting these two values, equation 1 and 2, that is delta G and delta G naught, in equation 3. Right? Put equation 1 and 2 in equation 3. What happens in place of G? Delta G, you can write minus NF E cell. In place of this delta G naught, you can write minus NF E naught of cell. Right? That only I wrote here. Right? Now this equation. Now multiply the whole equation by the minus. Means minus will become plus, plus will become minus. Now the equation is this minus will become plus, this minus will become plus, this plus will become the minus. Means I have multiplied by the minus. Right? Next, divide whole equation, this equation by NF. What happens? NF get cancelled here. It will, what is left here? E cell. Here also NF is there, divided by NF means NF get cancelled. What is left here? E naught of cell. Here it is. Next, RT by NF, because here there is no NF. Correct? Therefore, if you divide it, it will become RT by NF. Ln Kc as it is. Here ln Kc means here basis E. If you want to convert ln to the log, that is natural logarithm to the log base 10, you should have to multiply with the 2.303. Therefore, it will become, after multiplying 2.303, this ln will become log 10. Ln E becomes log 10. Now the equation is E cell is equal to E naught of cell minus 2.303. Why this one 2.303? Because I have converted ln E base E to the base 10. Therefore, this one is 2.303. Right? Into RT by NF log Kc by 10. Now we know that R, universal gas constant, fixed value 8.314 joule per mole per Kelvin. T is temperature at room temperature. What is the value? 298 Kelvin. F is Faraday's constant, that is 96,500. After substituting these values in the equation, after simplifying, we will get this equation. That is E cell is equal to E naught of cell minus 0.0591 by N log Kc. Right? This equation is known as Nernst equation. Now just remember this. This one is very important. It's very important. Now, once again, I am writing the equation. That simplified equation I am writing here. What is the equation? Just remember, very important. E cell is equal to E naught of cell minus 0.0591 by N. What is N by N? We will discuss later on. N means number of electrons involved in the reaction. Log Kc. Kc means what? Equilibrium constant. write the equilibrium constant for a given reaction? We will discuss first. How to write this Kc value for a given reaction. Now, you will see, for example, I am taking one general example. A plus B gives rise to C plus D. Now the reaction is at equilibrium. That is, rate of forward reaction is equal to rate of backward reaction. Just imagine this reaction is at equilibrium. Now how to write the Kc value? That is equilibrium constant. Equilibrium constant. That is, just remember, numerator you have to take the concentrations of the product divided by, that is, in denominator you have to take the concentration of the reactants. Here these two are the reactants, here these two are the products. Now how to write this? Here products are C and D, therefore I am multiplying concentration of two products. That is, here concentration of C into concentration of D divided by, here what are the reactants? Concentration A and B, therefore it will be concentration of A and concentration of B. This mark indicates concentration of that solution. Kc is equal to, right? Now concentration of the product divided by concentration of the reactant. Concentration of product divided by concentration of the reactant. That is equilibrium constant. Right? Now here nothing is there means 1. Nothing is there means 1. Here also nothing coefficient means 1. Nothing is there means 1. Therefore I can write here 1, 1, 1, 1. Correct? If these coefficients are not equal to 1, if it is A here, if it is B here, if it is small c here, if it is small d here, means AA plus BB gives rise to CC plus DD. Now what happens to the equilibrium constant? What happens here? Once again I am writing Kc is equal to, right here products are C and D, C and D. Therefore I am writing concentration of C into concentration of D. But the coefficient of C is small c is there. Therefore you have to write it over here C, small c. Right? Here, what is the coefficient of this product D? Small d is there. Therefore, you should have to write over D, small d. Right? Now, divided by, now concentration of reactant you have to write here. That is, A is one of the reactant, B is another reactant. Here, concentration of A into concentration of B. But the coefficient of A is small a. Therefore, here you have to write this whole concentration of A to the power small a. Here, coefficient of reactant B small b. Therefore, you should have to write here power B. In this way, you can write the equilibrium constant values. Now, I am taking another reaction, reduction reaction. This one is metal ion. Now, when metal ion, after gaining the n electrons, it will become n. This is reaction. How to write the Kc? Kc is equal to this concentration of only one product is there, therefore only M concentration of metal. So reactant is also only M. Only one is there, that is n to the power n plus m. That is metal ion. Here metal is the product, metal ion is the reactant. Therefore concentration of M divided by concentration of this metal ion, product by reactant. Concentration of product divided by concentration of reactant. Right? Now here coefficient is 1, here coefficient is also 1, therefore this one is the equilibrium constant. In this way, we can write the Kc values for the different reactions. How to calculate the electrode potential or reduction potential of the given half cell by using the Nernst equation. Right? Now that equation we are seeing now. For single electrode, it is half cell. For single electrode or single electrode potential. What is the Nernst equation that we are discussing? For single electrode potential or for determining the electrode potential of the single electrode half cell in electrochemical cell. Now, what is the Nernst equation we are discussing? Consider one reduction reaction. Consider any reaction you can consider. It should be reduction. Now, M to the power plus N plus N times of electrons. It will be reduced state. That is M. Here, M plus N means it is ions. Ions means which physical state is there? Aqueous. In aqueous physical state. Here, after gaining the N electrons, it is reduced now. It is M. Now this M is solid. Right? Now how to write the Kc value? Kc, we know that equilibrium constant for this reaction is Kc is equal to, already you know, concentration of product, that is M, divided by concentration of reactant, that is M to the power plus N, that is metal ion. That a product is metal, reactant is metal ion. After gaining n number of electrons by this metal ion, it is converted into metal. Right? This one is reduction reaction, gain of electrons, that is reduction. Now, this one is the equilibrium constant, concentration of the product divided by concentration of the reactant. Right? Kc value. Now, I am calling this one as equation 1. Equation 1. We know that Nernst equation. We know that from Nernst equation. What is the Nernst equation? E cell is equal to E naught of cell minus 0.0591 by N log Kc. Correct? Log Kc. This one is the Nernst equation here. Nernst equation. I am calling this one as equation 2. Now, put equation 1 in equation 2. Put equation 1 in equation 2. Just substitute this Kc value in equation 2, or substitute this Kc value in the Nernst equation. We will get E cell is equal to E naught of L minus, just here it is not for the cell, it is for the single electrode. Correct? It is for the single electrode, not cell concentration. It is electrode potential for the half cell. Half cell means I can write reduction value, means Mn plus N is converted into M here. Right? M plus N is converted into M. Here also M plus N, standard reduction potential of the metal M. Here electrode potential of the metal M. Right? Here E M plus N by M means it is the reduction potential of the metal at any concentration. Right? Now here standard E naught of M plus N by M means it is the reduction potential when the concentration of the metal ion is exactly equal to 1. Right? Now why I am writing only reduction potential? Because I want to calculate reduction potential value only. Right? If you write M by M plus N, it will become oxidation potential. Now just think here M plus N by M. This one is reduction potential. Reduction potential. If you write this one is M by N plus N, means here reduction reaction is there. This M plus N, after gaining N number of electrons, it is converted into M. Reduction reaction, gain of electrons. Here it is M is converted into M plus N, means loss of electrons. How many electrons? N electrons. Means so here it is oxidation potential. Reduction potential and oxidation potential for the same metal. For the same metal. This one is reduction reaction. M plus N converted into M by gaining N number of electrons. M is converted into M plus N. After losing a number of electrons. This one is reduction reaction, this one is oxidation reaction. Reduction potential, oxidation potential. If the reduction potential for the metal M is X, then oxidation potential will be minus X. Only that much is the difference, only sign difference. Magnitude remains same, X. If the reduction potential is plus, oxidation potential for the same metal is minus. Only sign changes. Just you have to remember. Here we are interested in calculating the reduction potential value. Therefore, I am writing it as M plus N by M, means reduction reaction. Now, here also M plus N by M, M plus N by M. Here, this one is the electrode potential of the metal M at any concentration. This one is the electrode potential or reduction potential of the metal M when the concentration of all the ions which are present in the solution is 1. Means 1 M concentration. Here concentration is any given concentration. Right? Not equal to 1. Now minus 0.0591 by N. Why I am writing N? How many number of electrons are transferred? N. Right? In this reaction, how many electrons are involved? N electrons. Therefore, I am writing here N. Number of electrons. Log in place of Kc, I can write it as M by M plus N. In place of Kc, I am writing here concentration of M by M plus N. Metal by metal ion. Here, if you see the reaction, here metal is solid. Metal is solid. Right? Now we will see first. Concentration of solids, that is metal. I am taking unit 1. Concentration of the solid in the Nernst equation, I am taking 1. Why I am taking 1? That is again tau is there. Correct? Why the concentration of solids is equal to 1? Right? Now, what is the reason? If you know the concentration definition, concentration is directly proportional to the mass of the solid, mass of the solid, right? A number of moles of the solid means what? Mass only, right? How much gram of solid is present in the given solution, mass, right? Divided by inversely proportional to the volume, inversely proportional to the volume means concentration is equal to number of moles by volume. I'm writing here mass by volume, mass by volume means when you increase the mass of the solid, concentration also increases. When you increase the volume by keeping the mass of the solid fixed, if you increase the volume, concentration decreases. Concentration decreases. Concentration is directly proportional to mass, inversely proportional to volume. Mass by volume means density. Correct? Density is equal to mass by volume. Means I can write it as concentration of any solution is directly proportional to the density. Density. For solids, density remains same. It won't change. For solids, density remains same. It won't change. Therefore, in place of density, I can write 1. It is fixed. It won't change. Means concentration of solids I am taking as 1. Therefore, concentration of the solids here it is equal to 1. For solids, also we know that concentration is directly proportional to the density. For solids, concentration remains same. Therefore, it is taken as unit. What will be the equation? E naught of m plus m by m minus 0.0591 as it is by m as it is. It will become log of 1 by m to the power m plus. Now, why I am taking this one as 1? This one is solid. Therefore, I am taking this equation is because this concentration of solid I am taking as unit. Then after putting this one, it will become 1 by m to the power n plus. Right? Now, it can also be written as this one is the Nernst equation for the single electrode. By using this equation, you can calculate the reduction potential or electrode potential of the any half cell by using this Nernst equation. By using this Nernst equation, you can calculate the reduction potential or electrode potential of the any half cell. Right? Now, you can write this one as, if you take this denominator n to the power n plus to the numerator, what happens? This sign will change. This sign will change. Means it will become plus, and this will become log n to the power plus n. N to the power plus n. Correct? Means is electrode potential is directly proportional to this one. Means concentration of the metal ions. That I am writing here. What happens when this denominator becomes numerator? This minus will become plus, or E of m to the power plus m by m is equal to E naught of m to the power plus m by m minus 0.0591 by n log. Now just check. I am taking denominator to the numerator. Means here it is m to the power plus n. What happens? This minus will become plus. Means when you increase the concentration of the metal ion in the reaction, here it is reaction. If you increase the concentration of the metal ions, here concentration of metal ion is increasing. Means this total value increases. When you add to this one, total answer will increase. Means this value increases. When you increase the concentration of the metal ion, indirectly the electrode potential is also increases. Means electrode potential or reduction potential of the half cell is directly proportional to the concentration of the metal ion. This one is fixed. N value is also fixed. Correct? Means therefore E of means electrode potential of the any half cell or reduction potential of the any half cell is directly proportional to the concentration of the metal ion for half cells. Clear? This is the formula which is used to calculate the reduction potential of the half cell. Or electrode potential of the any given half cell. If you given the concentration of the metal ion, just substitute this value here. Just calculate how many electrons are transferred. By knowing this one, you can easily calculate the reduction potential of the any half cell. This one is fixed, already given. Correct? Now, n value, number of electrons involved in the reaction. Now, here it is concentration. It is mentioned already in the problem, right? By putting all these values, you can easily calculate the reduction potential or electrode potential of the any half cell or single electrode potential by using this formula. It is also one of the Nernst equation for the single electrode potential. Clear? Now, Next, we will go for the complete cell potential. Single electrode potential over. For example, this one is the cell, this one is half cell, this one is another half cell. Both are connected with a voltmeter. Both solutions are connected by the salt which we have discussed already. Electrochemical cell by taking Daniel cell as example. Correct? Now, this is for single electrode. Maybe this left half cell or maybe for right half cell. You can use this formula. For complete electrode cell, electrochemical cell, what is the amount of voltage produced, total voltage or EMF, how much produced by the complete cell? It is also determined by using the Nernst equation. Not only half electrode potential or single electrode potential, you can calculate the complete electrode potential or cell potential of the given electrochemical cell by using the Nernst equation. That one only we are deriving. Means Nernst equation for the complete cell or cell potential. Now we will see that one. Now I am removing this one. Just remember this equation. E cell is equal to E naught cell minus 0.0591 by n log Kc. Now I want to derive Nernst equation for complete cell. That is Nernst equation for, I am writing here only, for cell potential or EMF. For cell potential. Here you have to consider in the electrochemical cell, already we know that one half cell undergoes into oxidation, another half cell undergoes into reduction. If you combine both, it will be redox reaction. Means in complete cell there is a redox reaction. There is a redox reaction is taking place. Right now we will see here. I am considering two metals. I am considering here. You can take any metal. I am considering here two metals. Metal 1, M1 and M2. M1 and M2. And just think that this M1, that is metal 1 is undergoing into oxidation. Metal 1 is undergoing into oxidation. Means it is acting as anode. Oxidation at anode. Anode oxidation. Correct? This metal 1 in the reaction is undergoing into oxidation. Just think I am considering that is acting as anode. This M2, metal 2, another metal is undergoing there in the reduction. In which reaction? Reduction reaction. Reduction always occurs at the cathode. Reduction at cathode. Correct? Now just consider M1 is the metal which undergoing into oxidation. That is, it is acting as anode. And M2 is another metal which is undergoing into reduction. That is acting as cathode. Right? Now we will see. I want to write the redox reaction. M1 undergoing into oxidation. Cell reaction. I want to write complete cell reaction. Right? How to write this? M1 is undergoing into oxidation. That is loss of electrons. M1 undergoes into oxidation by losing n number of electrons. I am taking n number of electrons plus n. M. After losing n number of electrons, it will become m plus n. Oxidation number is increasing. That is oxidation. Or here it undergoes into loss of electrons. That is oxidation. Now M2 undergoing into reduction. Correct? Therefore, reduction means here M2 plus n. This M2 metal ion, after gaining a number of electrons, it is converted into M2, means gain of electrons. M1 is losing its electrons, n number of electrons. Those n number of electrons are gained by the metal M2. Correct? After gaining M2 by n number of electrons, it is converted M2 plus n to the M2. Correct? Now here M1 only metal solid is there. Here M2 only metal solid is there. Here M2 plus n means it is in which state? Aqueous state. Ions are there in aqueous form. Aqueous. This one is the cell reaction. Right? I am considering two metals. Metal 1, metal 2. Metal 1 oxidation, metal 2 reduction. Here also M1 to M1 plus n oxidation reaction. M2 plus n to the M2. That is reduction. Loss of electrons. Here it is gain of electrons. M1 loss of electrons. M2 gain of electrons. M1 oxidation. M2 reduction. This one is the cell reaction. Now we know that how to write the equilibrium constant for this reaction. Kc, concentration of product. Here it is M1 plus M into M2. This is concentration of the products divided by concentration of the reactants. That is M1 by M2 plus M. I am simplifying here only. This one is solid, M2 is solid, M1 is also solid. M1 and M2 are the solids. For solids, what will be the concentration here? 1. Because the concentration depends upon the density. Density of the solids remains same. Therefore, the concentration of this metal solid M2 and M1 metal solids, correct? Therefore, equal to 1 unity. Therefore, it will become Kc is equal to M1 to the power plus M divided by M2 to the power plus M. M1 to the power plus M, M2 to the power plus M. Right? Now we will see. This is Kc values. Kc values. Right? Now we will discuss this. Here, it is for cell. It is for a complete cell. Therefore, we know that Nernst equation. What is the Nernst equation? E cell is equal to E naught of cell minus 0.0591 divided by N, because n number of electrons are involved in the reaction. Here, gain of n number of electrons. Here, it is losing a number of electrons. Therefore, n into log Kc. Log Kc. Correct? This one is the Nernst equation we know already. Now, it will become E cell is equal to E naught of cell minus 0.0591 by 10 log of, in place of Kc you can write, here it is M1 plus N divided by M2 plus N. Correct? Now, M1 is undergoing into oxidation, M2 is undergoing into reduction. That is product by reactant. Here, product concentration is how much? M1 to the power plus N. Reactant concentration is M2 to the power plus N. Product by reactant. Therefore, Kc will be M1 to the power plus N divided by M2 to the power plus N. By using this equation, you can calculate the electrode potential of the given cell. Electrode potential of the given cell at any concentration of the solutions. At any concentration of the solutions by using this Nernst equation. By using this Nernst equation. Or simply you can write E cell is equal to E naught of cell minus 0.0591 divided by N log of, right, M1 metal undergoing into oxidation reduction of just taking M1. We are observing that or considering that M1 is undergoing into oxidation. Means in place of M1 I can write oxidation reaction. Oxidation of the metal which is undergoing into oxidation. Now divided by here M2 is the, now I consider M2 as the reduction. M2 is undergoing into reduction divided by concentration of the metal which is undergoing into reduction. That is M2. Means this is also known as Nernst equation for calculating the electrode potential of the cell. Electrode potential of the complete cell. Electrode potential of the cell is equal to standard electrode potential of the cell. What is the difference between E cell and E naught cell? Here concentration of the given solutions is not equal to 1. Not equal to 1. For this one, concentration of the given cell is exactly equal to given solution is exactly equal to the 1. Right? When the concentration is exactly equal to 1, that is E naught of cell. When it is not equal to 1, that is E cell. Now, it can be calculated by using standard hydrogen electrode. E naught cell can be calculated by using standard hydrogen electrode. Here it can be E cell can be calculated by using this Nernst equation. Nernst equation. Now we will see. This is also another Nernst equation. Both are same. Here I am writing in terms of metal ions. Here I am writing in terms of oxidation and reduction. Or you can write M1 is the product. Just observe where M1 in the chemical reaction product. Correct? Product by M2 means reactant. Where M2 is there? Here M2 plus. Correct. Here it is reactant. You can write product by reactant. Product by reactant. This is also known as Nernst equation. Nernst equation. Clear? You can derive these two formulas by another method also, by considering only this reaction M1 to, right, by taking single electrode M1 oxidation, E oxidation, right, E of this M1 plus N by M1 is equal to, by taking this reaction at anode right? By taking this reaction at cathode, separately writing those two reactions and combining both reactions, you will get the same answer. You will get the same answer. This one is a simple derivation, simple one, right? Now, here E naught of cell. How to calculate the E naught of cell? We know that formula. E naught of cell is equal to, in the first class I given E naught of cathode minus E naught of anode. E naught of cathode minus E naught of anode, or E naught of cell is equal to E naught of, at cathode what happens? Reduction minus E naught of oxidation. By using this reaction also you can calculate the E naught of cell values. E naught of cell values. In case of problem, if he will give the E naught of cell value directly, you can directly substitute here. In sometimes what he will give, E naught of cathode is this much value, E naught of anode is this much value. In such cases, you have to determine this, calculate this E naught of cell by subtracting these two values. By subtracting E naught of anode from the E naught of cathode, you will get the E naught of cell. This is equation which is used to calculate the E cell value, complete cell value, and it is also a Nernst equation for the complete cell. Once again, you will see the formula. Nernst equations are formula I'm writing here. First, direct I'm writing Nernst equation. What is Nernst equation? E cell is equal to E naught cell minus 0.0591 by n, number of electrons transferred or involved in the reaction. Log of Kc. This one is Nernst equation. Nernst equation for single electrode. For single electrode, what is the Nernst equation? E of m plus n by m. It is not for cell, it is for half cell. Therefore, I am getting this one. M plus n by m means this m plus n, after gaining a number of electrons, it is converted into m. Gain of electrons means reduction potential is equal to standard reduction potential for the same metal minus 0.0591 by n log. There it is. It will be, I am writing minus means it should be 1 by m to the power plus n. If you are writing plus, it should be log of only m to the power plus n. Just remember this one. This is for single electrode. For complete cell, what is the Nernst equation? For cell potential or for complete cell, what is the Nernst equation? E cell is equal to E naught of cell. Now for complete cell, this one E naught of cell minus 0.0591 by n log of, here I am writing oxidation by reduction. Just remember the metal ion, the concentration of the metal ion which is undergoing into oxidation divided by the concentration of the metal ion which is undergoing into reduction. That is oxidation by reduction. This is for complete cell. How to calculate this E naught of cell? We have formula. E naught of cell is equal to E naught of cathode minus E naught of anode, or E naught of cell is equal to E naught of reduction minus E naught of oxidation. Carbo formula. Carbo, cathode minus anode. Rho means reduction minus oxidation. By using those two formula, you can easily calculate the E naught of cell values. Right now, here I want to take a few examples. What is the cell reaction for the Daniels? Daniel cell Zn undergoing oxidation, that is Zn plus 2 plus Cu plus contribution to reduction, that is Cu plus contribution to Cu. After losing 2 electrons by the Zn, it will convert into Zn plus 2, that is loss of electrons. Correct? That is oxidation. Zinc is undergoing into oxidation. Now Cu plus 2 to Cu means here it is already by gaining the 2 electrons. This is Cu plus 2 will gain the 2 electrons and it is converted into Cu. Now Zn to Zn plus 2 oxidation, Cu plus 2 to Cu reduction, or simply here Nothing is there means what is the charge? 0. Right? 0 to plus 2 means number is increasing or decreasing? Increasing. Oxidation number is increasing. Therefore, it is oxidation. Oxidation number is increasing. Oxidation. Oxidation number is decreasing. Reduction. Right? Now here 0 to plus 2. Therefore, oxidation number is increasing. That is oxidation. Zinc goes into oxidation. Here it is plus 2 to 0. Plus 2 to 0. In the reactant, oxidation number of the copper is plus 2. In the product, oxidation number of copper is 0. That is plus 2 to 0. Oxidation number is decreasing. Therefore, copper is undergoing into reduction. Now, zinc oxidation, copper reduction. Now, what is the last equation for this one? What is the last equation for this reaction or this cell? It will be E cell is equal to E naught of cell minus 0.0591 by n log of oxidation by reduction. The metal which is undergoing into oxidation divided by the metal which is undergoing into reduction. Those concentration you have to write. Now here it is oxidation divided by here it is reduction. Which undergoing into oxidation? 100% zinc. But zinc is solid. Therefore, we should have to take only this one metal ion. Concentration of the metal is unity. Therefore, you have to take just metal ions. Concentration of metal ion that is Zn plus 2. Oxidation. Which undergoing into reduction in this reaction? Cu copper. Therefore, it will be Cu plus 2 ion Cu plus 2 ions. Just remember. Another simple way. Product by reactant. You should have to take only ions. Product by reactant. Product by reactant. Product which is ion. Zn plus 2 is ion, not Cu. It is metal is there, solid is there. Ion is Zn plus 2. It is Zn plus 2 divided by reactant is Cu plus 2. Product by reactant. Product by reactant. Now, in place of N, here I can write 2. Why I am writing 2? Because how many electrons are involved in this reaction is only 2 electrons. This zinc is losing 2 electrons, minus 2 electrons. Correct? This copper is gaining those 2 electrons only. Therefore, here plus 2 electrons. Take anyone. Here, how many electrons are involved? 2 electrons. Therefore, I am writing 2. Right? Now, I am writing another example. Mg, Ag, Mg, Ag. If you compare the reduction potential values, this one is having lower SRP level. Right? Therefore, it undergoes into oxidation. Plus 2. Here it is plus 1. Plus 1. Right? Now, if you see this one. And then balanced equation. Now it is balanced. Now it is balanced equation. Here, one more very important thing. What is the coefficient of the zinc ion? 1 is there. Therefore, you should have to take power as 1. Very, very important while solving the problems. Right? You should have to write this coefficient as the power in the Nernst equation. In the Nernst equation. What is the coefficient of this Cu plus ion? That is also 1. Therefore, here power is also 1. Correct? Now here it is. For this one, what is the last equation? For second example, this one is first example, this one is second example. What is the last equation? E cell is equal to E naught of cell minus 0.0591 by N. How many electrons? N means number of electrons transferred. Number of electrons transferred. How many electrons are transferred? Mg is converted into Mg plus 2. Mg is converted into Mg plus 2. Plus 2 means loss of electrons. Plus 2 means how many electrons are lost? 2 electrons. Minus 2 electrons. Now here Ag is converted into Ag plus. Ag is converted into Ag plus. Means how many electrons it is? Wait, sorry. It will be Ag plus here. Because it undergoes into reduction. It undergoes into reduction. Gain of electrons. Here it is loss of electrons. This one is gain of electrons. Right? Ag plus is converted into Ag. By gaining how many electrons? 1 electron. Only 1 electron. Here it is 2 electrons are transferred. Loss of how many electrons? 2 electrons. But here Ag is gaining only 1 electron. Just think how many Ag are there? 2 Ag. 1 Ag is gaining 1 electron. 1 Ag plus ion is gaining 1 electron. But how many Ag plus ions are there? 2. Therefore, it will gain 2 Ag plus ions will gain how many electrons? 2 electrons. Means how many electrons are involved in the reaction? 2 electrons. How many electrons? 2 electrons. Therefore, in place of N, you can write 2. Because how many electrons are involving in the reactions? 2 electrons. Log of oxidation by reduction. Oxidation by reduction. Or simply product by reactant. Product by reactant. Here product are Mg plus 2 is there, Ag is there. Which one we have to write? Ag and Mg plus 2. I told already. Just write the ions. Here ion is Mg plus 2. oxidation Mg plus 2. The reactant, which one we have to write? Mg na Ag plus 1. Which one is in the form of ion? This Ag plus. Therefore, you have to write Ag plus. This one is correct formula, wrong formula. By saying, I can say that this one is wrong formula because here I have to write the coefficients also in the form of powers. Correct? Here coefficient of Mg plus 2 is how much? 1. Therefore, I have to write here it is 1. Here it is 1. What is the coefficient of Ag plus? How many Ag plus are involving in the reaction? How many? 2 are there. Therefore, I have to write here 2 power 2. Now it is correct. Correct Nernst equation for this cell reaction. Correct? Remember, always these coefficients are written in here in the form of powers. Written here 1 Zn plus 2 is there. That is concentration of Zn plus 2 to the power 1. If it is 2 is there, then it will be power 2. If it is 3 is there, power will be 3. Similarly for all the others. Correct? Here, how many Ag plus ions are involved in the reactions? 2. Therefore, here I have to write Ag plus to the power 2. If you write 2 Ag plus, it will be wrong. You should have to write it as Ag plus to the power 2. Already I told how to write the Kc. Same only. Correct? Now we will discuss relation between Nernst equation and the equilibrium constant. Last topic is it is relation between equilibrium constant and Nernst equation. Nernst equation. Or you can write it as equilibrium constant from the Nernst equation, or you can write it as equilibrium constant from the Nernst equation, or relation between equilibrium constant and Nernst equation. We know that already Nernst equation we have derived delta G is equal to some value minus NF P cell, delta G naught is equal to minus NF E naught of cell. Data from thermodynamic delta G is equal to delta G naught plus RT ln Kc. By using those characters, we have derived the Nernst equation. What is the Nernst equation? E cell is equal to E naught of cell minus 0.0591 by n log Kc. Log Kc. Correct? Or in place of this 0.0591, you can write as 2.303 RT by n. RT by n. I am writing n also. NF. That means 0.0591. How it will come? By putting the value of R, by putting the value of T, by putting the value of Faraday's constant 96,500. And after simplifying, you will get the 0.0591 by n. Right? Indirectly using this one. This one is direct. After simplification, we will get 0.0591 by n. Now, here at equilibrium, just remember. E cell value is equal to 0. Rate of forward reaction is equal to rate of backward reaction at that point, particular point. E cell is equal to 0. Means if you put the value E cell is equal to 0, you will get E naught of cell is equal to. If you take this one, it will become plus. Or if you take this side, it will become minus. Minus minus get cancelled. It will be E naught of cell is equal to 0.0591 by n log Kc. This one is the relation between equilibrium constant and Nernst equation. What is the equation? E naught of cell is equal to 0.0591 by n log Kc. This equation is very important while solving the NEET or JEE questions. He will give equilibrium constant for the reaction. He will give one reaction and he will give Kc value also. Right? After putting n, that is number of electrons which are involved in the reaction, by observing the reaction and substituting the Kc value, you can easily calculate the E naught cell value. E naught cell value. Right? If he is giving this E naught cell value and n value, you can easily calculate the Kc value. Right? He is giving two things. One thing you have to calculate. Right? If he may give n value and Kc value, easily you can calculate the E naught cell value. or if he is giving inert cell value and Km value, easily you can calculate the Kc. It is very important for solving the NEET or JEE questions. Then we will stop here. We will see in the next class. Thank you.